Yes, thank you very much, Ayrton, for this kind introduction. So I hope all participants, which I can not see right now, are up and running and can hear me well. I want to talk about how to build fail operational systems for autonomous driving. And actually this topic is so large that I pulled together a way too large slide deck. So I will I decided to show the full version here, but I will use some of the slides just as a short reminder. But you will have all the material available, not only on the video, but I also expect there will be a PDF file available in the end. So there will be a lot of information that you can also read afterwards if we don't touch every detail here today. So I just want to see if I'm ready for clicking to the next slide. Yes. So I have the nice role of being the Director for Lead Engineering and Safety, which Ayrton already introduced. And I would like to point out this has two major aspects in my professional world. One is, I would say, development-oriented and future new technology-oriented, but it also has to do with the real life, ensuring the safety in the real life projects and staying connected to the real needs of our customer projects with serious intent. So the key learnings that I want to touch today and I want to share with this webinar are related to this enormous complexity that we are heading for with autonomous driving. And it also means it's kind of a combination of complexity and also let's try to highlight this a little where I'm at. It also means that we have all kinds of safety challenges on the way to solve when we are heading for this complex, highly automated driving use cases. We will have to talk about building fail operational systems because the use cases that we are trying to use are heading more and more in the direction where aerospace actually has already been for quite a while. And we will talk about how to use principles from aerospace and space, but tailor them to the automotive use case and try to find a cost-efficient manner how we can translate them into the real world. And of course, this also means we have to talk about a software-defined safety platform because all this complexity needs some structure, how we organize it well. And this also means we have to handle real-time topics. We have to make sure we have highly heterogeneous environments under our view. And we also have to take into account how quickly hardware is advancing. And I will also dare to enter the area of architectural design, meaning we're not only talking about the electronic control units per se, but we will also talk about the overall vehicle architecture that is will be necessary for autonomous driving and majorly has to tackle these new challenges related to fail operational designs. So when we look at the automotive industry, and this is one of the slides that I think that we have already shared in one of the previous webinars, so I'll just rush through this quickly. It is evolving at high speed, and I've been in the automotive industry for quite a while. There's really a speed going on right now. We are moving from one function, one box, to something like a complex modular design with a lot of services being centralized. We are also seeing changes in the behavior of the OEMs, that they are cherry picking, they are selecting the best in class solution, and they want to get them from multiple different vendors, and they would not just choose one all-in-one supplier, but they want to have multiple different suppliers available to get the best solution. And we are increasing the speed of innovation cycles, looking at the enormous complexity that we're putting in there. We are really speeding up the process of getting designs into the field. And of course, this still has to match with the overall timescales of the automotive world. But it is, of course, a race, and there is a competition going on here to be the first one to provide a safe and stable solution with a large customer value. So in the end, the software functions are now going to be a key differentiator for the OEMs. And besides other things that are connected to a brand, maybe related to a specific design and look, we are now heading for software functions being the key differentiator that the OEMs want to compete on and want to show their expertise and bring this to the customers. So if we look at this evolving hardware architectures, we can already see there's like I would call it the N-box solution today, one box for one function, one control unit for one function, and we are moving towards domain architectures. This is majorly supported by the high computation power that the modern hardware electronics can provide. So these functions are compressed into a smaller number of very powerful ECUs, and it will continue in this area maybe in the range 2025 in something like an in-car compute platform, where probably something like 2 high computation platforms will be present in the vehicle. They might even need water cooling or something like that to handle this, but they will be compressing a lot of functions into high performance hardware. And if we do this, we do need a service-oriented architecture that can also fulfill real-time guarantees. This whole transition of multiple functions into one very large compressed high-performance hardware will only work if we manage to get all services and all real-time needs under control. So, and when we are now looking into the use cases that we want to tackle, we of course need a really solid safety approach, and we also have to enter this new area of fail operational to reach highly automated driving, majorly because we are partially or completely removing the driver out of the loop. So if we now focus on, let's call it hard facts determining complexity, we see all these sensors and all their diversity contributes to complexity. We also see a very high amount of information that needs to be passed between control units. We will have additional connectivity to the outside world. We heard about high definition maps. We heard about cloud connection. All these things need to be fed into this system as well. And we will have all kinds of clusters of applications running in parallel to do the navigation and the final controlling algorithms. So for me as a safety guy, I have to say complexity is one of the key challenges when we are trying to get safety well done. We really have to keep an eye on the complexity. And these challenges coming along with the sensors also means we will probably see multiple different combinations of sensors being used, because due to certain weaknesses of the one or the other, we will probably not see just a one-size-fits-all solution, but we will probably always see a combination of sensors, and this is the key to make it really usable and safe. And of course, the fusion of all these sensors is an important and challenging task, and it has real-time requirements as well. So with a new architecture approach, we do also have some opportunities, and I think this is the part which has already been covered in detail in a previous webinar, so I'll really brush through it real quick. So one of the first things is boost of return of investment. We want our software to be written once and used through multiple projects, even if the hardware and everything changes. We want to have a seamless roadmap from certain degrees of automation to full automation in the future. We don't want to throw all this development work away and start all over again. We want to have some cost predictability, so we have to make sure that when we put it all together, we don't end up with unforeseeable additional efforts. And we have to have all these development and deployment risks under control with all the necessary defensive measures in place, like getting complexity down wherever possible and getting the real-time requirements really settled. And in the end, the key of all this, let's call it setup of the development environment, is to accelerate the time to market so we can get these things on the road, maybe with a reduced functionality at the beginning and with a higher functionality later on. So this aspect of scalability is in there all the time. And with all this, let's call it soft facts in the background, we have to think about what are the right ways to do this and which challenges are the ones that we want to tackle. So I'll start with some of these challenges you already heard. Time to market, we need real time, we need scalability, we need guarantee of service, and we will deal with a high complexity here. And on top of that, we need safety. So we have all kinds of different criticality levels to be nicely separated independently and running on the available hardware. And we really have to watch out that wherever we introduce additional functions, that we still keep our real-time targets achieved, because this is one of the key things that is even much more relevant for the automotive market than in aerospace. The real-time requirements in automotive are really tough because the reaction times of an overall system like a car are really short, while an airplane flying in mid-air does have some relaxed timing requirements compared to this. Yeah, and we will enter this world of fail operational, and I will share some more slides on this, meaning that when we design the system, we always have to design it in such a way that even in presence of a fault, we can continue operation. And actually, this calls for a complete redesign of the existing fail-silent architectures, but we probably just don't have time for that. So we have to find a migration path from the fail-silent world to the fail operational ones. And I think there is a hard barrier just between level 2 and level 3 of automation. So if I use the SAE classification here, we see a big jump actually in handing over responsibility from the driver to the system, to the electronic system, moving from level 2 to level 3. And this means we cannot rely on the driver as the fallback that will take over in all cases. We have to at least consider a certain takeover time for this driver. And even if it's only a few seconds, it will put a strong burden on the electronic system that even in presence of a fault, it can continue operation. And I know these levels 0, 1, 2, 3, 4, 5 look like a very even staircase, but on the aspects of safety, we have a big jump between level 2 and level 3. We need to tackle the fail operational requirements, and that is a whole story on its own. So to focus on the translation of what does this mean for the driver and for the system, I would like to point your attention to this line we call fallback here. Driver is the fallback, driver is the fallback. Here it starts, driver is the fallback after a certain takeover time. For defined use cases in level 4, the vehicle is the fallback and has to handle everything on its own. And for level 5, we don't even have to discuss. Yes, of course, the system has to handle all cases autonomously. So if we look at the architectures that we will need for this, we can assume that these architectures will have something like an introduction of additional redundant components. And we will also expect that there will be higher ASIL levels coming into the game. And we try to indicate this with just some generic pictures here. saying an assumed architecture for a level 2 system can be quite simple based on a single SoC, but when we move to level 3, we will probably talk about 2 independent control units, and they will have different SoCs inside and perform a combined function. And as we advance to level 4 and level 5, the amount of functionality that can be handled by these control units increases and will probably lead to a quite symmetric approach in the highest level 5 version, where we will have very high performance hardware in at least 2 different control units. These units might not necessarily be separated into 2 different housings. This is more like an architectural view here. But in the end, there will be, of course, a strong need to create good fault containment regions to make sure that the fault does not propagate from one to the other. So the complexity is a tough thing. Now the redundancy comes on top, and to make it all safe is a really big challenge. So if we look at these level 3, level 4, level 5 use cases, what is the key aspect of really formulating a requirement resulting from fail operational? And I would say the most obvious case is if we enter the range of high speed and we are using a system like a highway pilot. It has to, in case of a fault, it will probably request takeover to the driver, but this will take some time. And during this time, it has to still be capable to do some at least reduced level of operation. And even if the driver does not take over at all, it still has to perform some kind of a reasonable continuation of the functionality. And this is a big change to today's fail-silent systems, where you would get a red lamp indicating a certain system is not working, and the driver then has to be capable in the same second to handle maybe loss of steering assistance or things like that. And he can do that because he is the fallback in himself. And of course, if we move to level 5, we're not talking about 10 seconds, we're talking about the whole mission time being available with this functionality. So we talked about these challenges. Availability is now a big topic. We have to make sure the system stays available. Maybe this is achieved by using some redundant components. We also have to watch out that wherever we want to achieve a high AC level, we have to achieve this in combination with the fail operational requirement. So we cannot just always introduce a strict monitoring and switch to the safe state whenever it happens, because the safe state is not really safe anymore. The system has to stay capable for operation. And actually, we see additional challenges that the AI-based deep neural networks do not really have a clear safety argumentation how we can justify that they are now safe and ready for release for public roads. And we will need these redundant elements, and the vehicle architecture has to reflect the design principles to stay away from common cause faults like losing power. So we will have multiple power domains in the car, and we will have architectures that are to some extent separated and are capable to continue in a fallback mode, even if there's no driver that we can rely on. So when we do this in the real life environment, we will find out that the faults that can happen at an arbitrary complex situation, maybe a situation where normally driver handover would be requested immediately, like some unforeseen construction site, people on the highway running around, things like that. So when we reach a certain speed, like highway speed, we're talking about 360 meters of travel that are covered in 10 seconds. And during this time, we cannot just blindly continue what we have been planning before. We have to actively react to other situations and other participants of the traffic. So we will have to have something like an active and a fallback system in place. and we will have to provide sufficient computation power on both of them to actively control the driving situation when moving on. So if we look at this as a cross-industry situation, you will see, well, there are industries that are perfectly fine with fail-silent designs, and this has, I think, can be nicely mapped to the different industries that we as a company, TTTech, are working in. For the off-highway market, fail-silent is perfectly fine. So in case of a fault, all the machine has to do is to stop and everything is fine, all dangers are gone. In the industrial world, we want to keep the availability of the system improved for availability reasons. In automotive, we're now moving in this direction, fail operational more and more. And in aerospace, of course, nobody is doubting that the aeroplane has to be fail operational, and it's not acceptable in case of an electronic fault that the whole airplane will crash to the ground. No, it has to continue operation. And actually, we are heading in the same direction when we're going for autonomous driving with the automotive use case. So there is some cross-industry experience that we can rely on here inside TTTech. But as I said, we still have to adapt these things to the needs of the according market. So after talking about all this trouble, I would also like to talk about solutions. So we do think we have some of the building blocks of these solutions in place to make really fit for purpose designs. So I tried to compress this into this slide by showing all these challenges we already talked about. I'm not going to repeat them. And we think the main building blocks of a good solution is, first of all, to have an open integration platform where you can pull all kinds of different software components together in a safe and controlled way. You need to make it modular in the sense that this architecture that is built into the car can grow. It can be ranging from small vehicles to large vehicles with more functionality. And no matter how complex the system is, we always have to make sure that the real-time capabilities are fulfilled. You could imagine that a complex sensor evaluation that does detect a pedestrian coming out on the street, appearing behind some obstacle. If you have all the computation power to calculate it, but the result appears too late, you will probably already run over that pedestrian and you will not take the benefit of the electronic system detecting him. So you really have to make sure you not only detect him, but you also get him detected within a very strict time constraint. And the safety we want to claim for the overall end product has to be built in there by design from the very beginning. So one of the solution elements is what we call real-time orchestration. So we need a deterministic behavior. We have to have guaranteed latencies, not only for the communication, but also for the execution of software. In the end, we want to provide end-to-end guarantees across a heterogeneous environment, from the sensors through the processing all the way through to the actuators. And in the end, these computation chains have to be very strictly designed and monitored during the development process. So if you assume function 1 and function 2 to being deployed on a complex high-performance hardware, you will probably end up with these functions being split into different hosts. Maybe some safety-related functions go on the safety host. Other functions need high performance, go on performance host 1 or performance host n. And no matter how you distribute these functions, they will talk to each other using input and output messages, also intermediate messages, and you will need some kind of communication backbone to exchange this data. In general, this is already well known, but we are moving this to a very high level of complexity now when we integrate many functions and also a lot of data flowing between them. And it's not enough just to put them there. We have to have the global scheduling, the end-to-end real-time guarantees, and this deterministic behavior that we can really rely on the results, we have to design this into there from the very beginning. The second element is what we call the open and modular integration platform. That means we will see like AutoSAR Classic and AutoSAR Adaptive APIs. We will try to find ways how we can integrate different applications onto a same uniform platform, and also create digital twins for software in the loop co-simulation environment, because we are already in this range of complexity not capable to kind of develop the whole thing in one shot. It has to be co-developed using all kinds of platforms for the development work and to combine them. So in the end, we will end up with certain functions being swapped from one host to another, being moved around when the platform is reused for a new version with a different scaled performance level, for instance. And so we have to have the opportunity to use standardized APIs so we can reuse the application software developments when we move them across different hardware, or we advance from one performance host to another generation performance host in the future. So we do anticipate that sometimes the communication will be on a board internally in a control unit, but sometimes it will be separated on purpose. It will be hosted in a different control unit, separated from the others. So we have to have a solution where we can share this information across a communication backbone, even if they are physically separated. And of course, this just means that the concept of a safety platform has to consider these multiple different, let's call it, architectural layouts. Yeah, and with this, we also support introducing fault containment regions to support the fail operational system designs, because you can imagine if you have a certain power supply supplying the high performance control unit over here, you will have to have a solution. What can you do in your vehicle if this power supply fails? And then you will probably argue, I have a second power supply and a separated control unit that will then take over this functionality. And of course, the communication backbone will then be limited, but it will still be available if it's not just based on one single pair of wires. The third element of fit for purpose is what we call safety by design. So here, actually, all these building blocks that are well introduced in the ISO 26262, freedom from interference, designing according to high-level standards, following an ASIL-D compliant development process. All these things are necessary, and you also have to be capable to handle errors with the high ASIL level. So this is a big jump, actually, comparing fail-silent designs with the fail-operational ones, because now error handling is not just informative for some repair activity. Error handling is now a key property of ensuring the fail operational capability of the overall system. So to do this, we are going to introduce barriers. This is not really new, but these barriers are, I think, the key element to get this freedom from interference done. And freedom from interference is actually quite a complex thing. It's not just based on timing alone. We have to make sure that we have the right timing in place for all the different bits and pieces of the application software that need to be executed, and also their communication need. We also have to have the memory that they use nicely separated, and we do want to use this memory also for exchange. So we need some kind of a smart way to keep the barriers in such a way that we get freedom from interference, but we do have an allowed exchange of data and flow of information through the safety software platform and the communication backbone that it uses. Okay, and to really unleash the benefits of all these solutions, there's kind of the need now to talk about the product we call MotionWise, which is a highly modular scalable platform and has all these things already designed in there. And it is based on exactly these principles that I have just explained right now, including the safety by design. And it is developed following an ASIL D compliant safety development process. So if we look at a reference architecture now a bit more concrete, what kind of sensors do we see? What kind of actuators are we going to control? What kind of functions are in there? We probably can expect there will be a lot of central processing going on in some kind of central ECU. Maybe this ECU will also be split into multiple ones, and we need a communication backbone to hold it all together. And I'll rush through these here because this is actually history. There used to be a time where there was a lot of glue code needed. Then some OEMs tried to reduce this. What we are proposing is to use the MotionWise platform that is capable to handle the AUTOSAR Classic RTE interface and also the AUTOSAR Adaptive interfaces, and provide a platform that supports all these different APIs and still delivers real-time guarantees. So with real-time orchestration, safety by design, and open integration platform in there, we have, of course, developed all kinds of detailed building blocks inside. I'm not going to try to present all of them here today, but we think this is the right kind of super operating system, let's call it this way, to orchestrate all this across multiple control units, multiple hosts, maybe separated across some different control units. And depending on the complexity in the sensors and the complexity in the actuators, there of course might also be a reason to integrate MotionWise into them. Of course, if the sensor is, let's call it, just providing simple raw data, this does not really make much sense. But if there's a pre-processing activity there that needs to be nicely synchronized to the next step of processing, maybe here, then this, like the data fusion, then it does make sense to synchronize this activity in a certain sense, and MotionWise is also capable for integration into multiple different hardware platforms. So I'll really have to speed up now. So there's high performance computing. We expect safety and performance hosts side by side. And this is also reflected with the existing chips that we see. Maybe some of them already have combined the safety host and the performance host or cores inside one and the same chip. This does not counteract the concept. This actually supports the integration into even smaller hardware. But when we look inside MotionWise, we now have these three basic blocks in there. I'll start with the core. The core has scheduling services, communication services, time synchronization service, and this, what I would call safety and health services built inside. So this is actually nicely covering all these generic safety topics that we mentioned. We will also provide some extensions. Extensions can be things like automotive lifecycle management, logging and tracing, and things like that, or a black box recorder. These are parts that we call extensions that we also offer in this platform, and they make sense for the automotive use case. And of course, the whole thing also has to go with tools. So we're not only talking about the embedded part, we also need some tooling to create the software. We also have a software development kit that we offer so our customers can create their own complex system based on the MotionWise platform. And they, of course, also need a software-in-the-loop environment to be able to do their testing and simulation and all this. And of course, we support this with the right kind of software-in-the-loop library to execute these things on a PC, to speed up the development process. So I'll rush into the fail operational topics now. The very simple view of the driving task we are doing is reading sensors, perform some kind of automated driving system, and then providing the outputs to the actuators. Now, this is just kind of the most abstract view I can think of to sketch this. But in a failure-free case, we expect this system to intelligently whirl around obstacles. But in a failure case, if it just stops working and continues driving at a high speed, just keeping in lane, this would be not acceptable. So if we confess that this automated driving system can fail, we're actually in real trouble, because this will cost people their lives. They would get killed if the system would be built in this way without any redundancy. So the first idea is, okay, let's take two. Let's just take two of them, and then we run into a new problem that automated driving system 1 and automated driving system 2 might have a different view on how the correct driving trajectory looks like. Both of them are valid, but they don't agree. So if we take two, we will end up with the problem that we just cannot do a simple voting. And even if we add a third one and say, let's do majority voting, we might run in trouble that in complex situations, we might even have three non-agreeing but all valid results. So we need a different model. We need something, I like to call this the happy marriage model. Happy marriage meaning, in a normal case, it's the active partner determining where to go. But if something goes wrong, there's a fallback. And if you're married, you probably know if you're the active or the fallback. So that's kind of different in every relation. But it has this general idea of, I have a complex activity done by the active control unit. And in case of a fault, I go to a more conservative fallback strategy. And I think this is a reasonable approach, and we can handle it with diverse cameras, diverse sensors. We can handle it with different driving algorithms on the active and on the fallback side. They would probably be less aggressive on the fallback side. And of course, when we come to the actuators, we will have some kind of redundancy there too, but I'm not focusing on that today. That is actually a topic that is well handled by the actuator suppliers today, and they are on their way to provide failed operational actuators. But we will end up with this topic that there will be conflicting outputs coming from active and fallback. And one method to resolve this is to select first valid, meaning always take the active input and only if it's not available, take the one from fallback. So if we now look into the complex task of developing a automated driving system and bringing it to the highest ASIL level, ASIL-D, we actually need an additional ASIL-D composition inside this one active branch. And here again, the method of splitting it into two and just comparing if they're calculating the same result will not work. So this symmetric approach is not feasible. It will not work. It will fail. So the alternative is to move into an active checker mode. Some like to call it a doer and checker. Some like to call it a command and a monitor. And actually, these are principles that are well known. Here again, I would like to call it something like the happy marriage, because the active person needs a supervisor checking what's going on with your outputs and am I confident that that is correct. And this active and checker approach might also be something that you can see in airplanes with a pilot and a co-pilot. So that's why we use the term co-pilot for our idea and for our ongoing development right now. We call the safety co-pilot would be a functionality that actually would be located inside the primary node to make sure that the primary automated driving system is always monitored when it creates outputs. And the main idea here is to get these outputs to be correct, meaning if they are not correct, there is an intervention, and the intervention is to silence the primary node and to then switch over to the fallback. So in principle, we have two acyl decompositions here. If you look at it in detail, first we split it into primary and fallback node, and inside the primary node, we spend a lot of effort to get the outputs correct. And I think this is absolutely necessary because we will have very complex primary automated driving systems, and they will use neural network algorithms in there as well. It does make sense to develop the safety copilot to just do verification of these outputs and use the benefit to make it a bit simpler and a bit different, and with this diversity, get correctness on the outputs. So that's the general idea here. So if we look at our MotionWise platform, we are now actually talking about an application module on top of the MotionWise platform that I would call the safety copilot, or you might call the checker in a different, sorry for this disturbance here. So inside the safety copilot, we will have a kind of sensor processing and sensor fusion. Maybe it will be a bit simplified compared to the full primary system. We will have verification modules and a decision maker in there. And we're working on this. And we think this is a valuable extension to our platform and can be used to not only benefit from this acyl decomposition and offload the high acyl level from the primary automated driving system development, but also to get a good safety argument in the overall use safety case in the end. Okay, so what we want to achieve with this is to get the correct behavior out of this highly complex primary driving system. So we think this is also a seamless roadmap to full automation in the future, and also into further integration on the hardware level with in-car compute platforms coming along. So just to give you a rough idea, we do expect that there will be, let's call it smart IOs inside the vehicle, doing the actuation, doing maybe also the sensing. But we will end up with some high performance in-car compute platforms, probably two of them in the vehicle, doing a whole variety of software implemented functions. And of course, they have all the requirements of handling this internally in the vehicle, but also communication to the outside world. So if we look inside, we see that we have different worlds coming into this same in-car compute platform. We have what I would call the connectivity, infotainment, visualization stuff, but also the hard real-time safety-related stuff. And we will have to find a way to host all this on the compute platform with sufficient independence between them and ensuring freedom from interference, so these mixed criticality levels of functionality can be executed, all sharing, let's call it the same high performance computation platform and also a communication backbone. So in the end, with MotionWise and the safety copilot, I think we have some nice benefits that we can point out. We have all these safety mechanisms in there that are suitable for this sophisticated redundancy needs that we have when we're moving towards fail operational. We have the design ongoing and already fulfilled to a large extent with ISO 26262 ACLD compliance. And this supports also acyl decomposition in the application software, especially to get the acyl level down to an acyl B from D and another acyl B from D. So you can that way reduce the acyl level for the individual parts of the application software. And of course, it supports a deterministic time triggered architecture, because that's exactly the let's call it the key element of our operation inside this company. And it is majorly, let's say, influenced by the aerospace industry, but it is applicable to the hard real-time world of automotive just as well. Okay, So we do think we are a reasonable partner, and I do want to point out that this MotionWise stuff is not just a paperware. It's in fact already on the road. The product that we have developed here has already reached series introduction with this beautiful Audi A8 here, and also multiple other versions in the VW Audi consortium. And it is an enabler for these parking pilot and traffic jam pilot functions that are available today. And so we do have some additional benefits I would like to point out here. I'll skip this. You can nicely read through this. I do want to point out that cross-industry experience is a benefit to learn from other industries and to incorporate it into new use cases. That's exactly the key work we are doing here, and that I am involved in TTTech Auto. So actually, this is, I think, my final slide. I think a little bit over time. So it helps to our customers, organizations, to get away from slow and costly development into a quick integration process. No surprises when integrating the software because they're nicely separated. This is a key element of speeding up the development process. And together with the co-pilot, we get an end-to-end safety approach available. And in the end, it is also a roadmap to full automation in the future. It starts off with a certain degree of automation, but can move further. And it is also capable to move to an even much more high-performant hardware platform like in-car compute platforms in the future. So the idea is to accelerate this journey by using things that are already available, like the MotionWise safety platform and the safety copilot. Thank you. So I think now we're ready for the Q&A session.
Yes, we are. Thank you very much for your presentation. We are ready. We already have a few questions for you. So let's make use of the last few minutes that we have and dive right in. The first question would be, what would you consider the largest challenge when moving from fail silent to fail operational?
Well, on the first look, it is to make the system available under all conditions. So availability now becoming a safety property is a big challenge. But quite often people think, oh, that's no problem. I'll just throw hardware on the problem and just put multiple of them in there. But that's not enough. I think the largest challenge behind this availability topic is to get the complexity under control, because this enormous complexity is the real dangerous part where faults can come in and violate safety goals. So getting the complexity under control, using defensive measures to get complexity down, that's the key topic when we move for fail operational.
Thank you. And do you consider additional redundancy of safety functions as a cloud service?
Well, I think cloud services can contribute to safety in a way that they can add additional information. So with a cloud service, we can have access to additional information, but I would like to have the view that this is an additional kind of sensor that is more complex than just a camera, and introducing additional available information into the overall process of doing the in-the-car decision making. I would say the cloud computing is like a very complex sensor that is incorporated into this. So it has to have a local representation in the vehicle that is real-time capable, and it has to have a safety-related content in the background that is available through the cloud. So I would consider it safety-related. I would consider it as one additional sensor contributing to the overall safety.
Good, thank you. And does your platform allow customized software architecture to achieve lower automotive safety integrity levels, or does it enforce level D only?
No, this is exactly what I tried to point out in the slides. We are totally aware that the application software that is developed and is used will be of a mixed criticality level. It will also be of mixed, let's call it performance levels. It will also be of mixed real-time requirements. Some things will have very strict real-time requirements, others will have a more relaxed real-time situation. And we are ready for this in the sense that the platform is capable to support all the way up to ASIL D, but it does allow individual pieces of the application software to be other ASIL levels and also to be QM, because we actually are aware that we have to find a way to combine all of them. So this was a design target from the very beginning and is already implemented in the existing MotionWise implementation today. From ASIL D to QM, all are represented there.
Great, thank you.
May I add, of course, for the platform, this means it has to be ASIL D capable. There's no excuse for the platform to say, well, I will only support up to ASIL B. That will not be sufficient. So the platform requirements is very strict because it has to support the highest ASIL level. But of course, the application software components shall be of the ASIL level that is appropriate for them.
Good, thank you for that addition. Then I think we can move to the next question, which is how can a detection algorithm of obstacles be considered as safe in your architecture? And what has to be done to check the results of the algorithm?
Yes, I think this is a good question because this is the critical point. And I think I can only provide one major element of the answer. It will not be the full solution. But I think one major element is we need a certain kind of diversity, not only in the raw sensors that we use, but also in the way how we process them. And I would even claim that this is exactly what the human being does as well. Because while performing the driving task of simple driving a car, which everyone from us has already experienced, you are not aware that you are actually performing multiple processing activities in parallel. So this parallel activity of just looking at the contrast, just looking for objects, just looking for things that are approaching me, looking for things that are unusual, I would say all these things are happening in parallel, and this is exactly what we wanted to point out with the Safety Copilot. The idea is not to do just exactly the same thing again, but to do it in a different way, maybe using slightly different sensor inputs and processing them in a different way, maybe on a more conservative algorithm, and use the combination of these to determine if the output really is correct.
Good. Then the next question is quite brief. Is V2X missing? No need for autonomous driving level 4 and 5?
Well, in a certain sense, I indicated communication to the outside world in some of the slides, but you're right, I did not emphasize this very much. I would consider vehicle to X communication as something that is reasonable and valuable, but it is, as I said before, probably only one kind of sensory information that we can add. We will probably never be able to use this as the only source for decision making of autonomous driving. So I would consider it as part of the overall architecture, but it is kind of, I did not focus on this very much, but it would be like an additional aspect of the sensory inputs going into the vehicle. And of course, there might also be some relevant outputs that then have to be created in an application layer to be communicated to the outside world.
Okay, and with the time in mind, maybe we will take one or two more questions in before we hand over to the next presentation. So can you explain how the Copilot, while being more simplistic in its design, would be capable of second-guessing the performance unit's decisions?
Well, I understand this question. How can that be, right? And one short answer to it is, well, criticizing an output is easier than creating one. So it is a general idea of the Safety Copilot to really focus on monitoring the correctness of the trajectory and not trying to calculate its own, because that would be redoing the same task again. It is part of the concept to focus on the monitoring of the free space and not trying to calculate the trajectory again. And I think this is a reasonable concept that reflects the human way of operation as well. One very complex task is to take a decision, and then there's a second kind of layer of monitoring if it's okay. And this monitoring layer is, of course, not easy to do, but it is a simpler task than the first one.
And then maybe the last question, your proposal is to run the same fusion trajectory generation software on the primary and fallback ECUs?
No, actually I would not propose that, but this is actually already a tricky question. I would say if we consider the simplicity that we are trying to get into this complex task, we will probably end up with the fallback being not exactly the same as in the primary. That does not mean that there might be some things that can be reused, but we really have to watch out not to create a common cause fault here. And this common cause fault topic is exactly the critical item that needs to be looked at very carefully when deciding which piece of software can be reused on the primary side and on the fallback side. In general, I would say I could imagine a solution with very similar software, but the software operating with different sensor inputs or with a different granularity. That would be a suitable solution, but I would be very careful trying to do a one-on-one copy when we are not sure that the first implementation was really correct.